Hello engineers, welcome back. In the previous video, we solved a Leet code question on binary trees. In this video, let's pick up a question on binary search trees. Okay, I hope you're ready. Let's get started. So this is the question we're going to solve today. It's called validate binary search tree. So let's understand the question and we'll see how we can approach this. So given the root of a binary tree, determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees, right? So let's see how this looks like. So let's take this example. There is a tree here with root node as 2, and then we have 1 on the left side, 3 on the right side. Because 1 is less than 2, it is a valid left subtree, and because 3 is greater than 2, it is a valid right subtree. So overall, this is a valid binary search tree, so we return true. Now let's see this example. We have 5 as the root node, and then we have 1 on the left side. Because 1 is less than 5, this is a valid left side. Now let's look at the right side. We have 4 on the right side, but as per the rules, the right subtree should have values greater than the parent, right? That is why this is an invalid binary search tree, so we return false. Okay, so that is our question. We need to validate whether both the sides are valid binary search trees. So let's see how we can approach this. Let's take this tree as an example. Okay, so this is our tree. So let's see what is the approach and what are the conditions we can apply. So let's look at it from root's point of view. So from root's point of view, what can be the possible values for left node and what can be the possible values for the right node? So what is the first condition? The first condition is that from the current node, the left child should be less than it and the right child should be greater than it. So that is our first condition, right? Left child should be less than node and right child should be greater than node, right? So this is our condition. And secondly, the entire subtree should have values only greater than this node. The entire values in the left subtree should be less than this, right? So the same condition not only applies to the current node and its immediate children, but it applies to all the children and grandchildren as well. Children and beyond, we can say, right? Every node in this side of the tree should be less than this, and every node in this side of the tree should be greater than this. So what is it coming to? It is coming to the point that every node can only take a certain range of values, right? So if we look at it from this node's perspective, let's look at it from this node's perspective. What can be the possible values of this guy? So what is the range? What is the minimum value that it can take? What is the maximum value that it can take, right? We are talking about the left node. So minimum, there is no limit, right? It can go to 0, -1, -2, -3, and so on. As long as it is less than 5, we are still okay, right? It still is a valid binary search tree. So the minimum value is, let's say, -infinity. And what is the maximum value? Maximum value is 5. It can only go up to 5, right? Now let's look at this guy, the right node. What can be the minimum and maximum value? The maximum value can be anything, right? It can go to 6, 7, 8, 9, 100, 1000, 10,000. So there is no upper limit on the right node. Upper limit can be infinity. And what is the lower limit? Lower limit is 5. It has to be minimum of 5. So greater than 5. Here on the left node, the maximum value can be 5, right? So this will be our condition for every node. So what is the condition? For the left side, there can be a minimum of -infinity to current node value, current value. And on the right side, minimum value should be current value, and it can go all the way up to infinity, right? And because we don't have the concept of infinity in programming, we can use the concept of, the int max and int min, right? We have these variables given by the C++ language. We can use them. But if you look at it here, the value can go all the way up to 2 to the power minus 31 and 2 to the power plus 31, right? So our int max, int min may not be valid for all the cases. So instead of int, we will use long to accommodate for all the possible ranges given in this question, right? So what will be the approach? So programming approach will be like this. We need to go to every node and check whether they are following these conditions or not, right? So if it is a left subtree, is it following the condition given here? If it is a right subtree, is it following the condition given here? So we can use the concept of recursion for this. First, we will go on the left side, check every node and check if it is in the range. If it is in the range, we will move on to its children. If it is not in the range, we can directly return false. Okay. So let's see how we can code this. So let's say we have a helper function. Let's call it check. And for this, we will pass our root node first. And what are the possible values for the root node? Root node can be anything, right? It can be minus infinity to infinity. So we can pass in long min and long max. It can be anything. Okay. And whatever is the answer coming out of this helper method will be our answer. So let's create our helper function. Let's do root check and let's take in a node. And we will take in a long value. Let's call it minimum value. And another long value, let's call it maximum value. Okay. So since we will use recursion, we will need three things. First is the base case. So if we hit the depth of the tree, we can stop recursion and come back. So if node equal to null ptr, we can return true, because we have safely traversed the whole tree and we have not found any issue. Now let's implement our recursive case. What is the recursion? First we go down the left side, node arrow left. For going down the left side, what is changing? If you look at it here, now we have minus infinity to infinity as min and max. So if we are going on the left side, what is changing? Our minimum value is not changing, it is still minus infinity, and the maximum value is current value. Current value is the node 5. So whatever is coming here. So min value is still min value, no change, and max value is node value, current value. Okay. Once we go down this tree, we can come back up and go down the right side. For right side, what is changing? Let's see. The min value is changing to current value and maximum value is still infinity, right? So min value is node val and max value is still the same. Okay. So we went down the left node, we went down the right node. So these are our recursion calls. And what will be our operation? We need to check if both of them are true. If both of them are true, we will return true. Otherwise, we will return false, right? So we will just need to add our main condition. What is the main condition? For every node, we need to check whether it is in the given range, right? So what is the range? Min value, max value. So node val should be greater than min value and node val should be less than max value. This is our condition. If this condition is violated, we need to return false. Simple. Return false. Right? Quick recap. What are we doing here? for every node, we are checking whether it is falling in this range or not. This is the accepted range, right? If it is on the left side, this will be the range. If it is on the right side, this will be the range. For every node, we are checking this condition. If that condition is failing, we will return false. Otherwise, we will go further down the tree. Okay, once every node is parsed and traversed, we will simply return true. Okay, anywhere in between, if there is an issue, we will return false. So that is our logic. So let's run and see. Accepted. Let's submit. Okay, our solution is accepted. So what can be the time complexity? Time complexity is O of n basically, because we are visiting each node at least one and then comparing it with a given range, right? So this is O of n operation. So that will be the time complexity. So I think that's it for this video, guys. Thank you so much for watching. I hope this question was helpful to understand binary search trees. So if you have any questions, definitely ask me. Don't forget to like the video if you found it helpful, and don't forget to comment if you have any questions or suggestions. Please subscribe to the channel and bookmark the playlist and share it with your friends. Thank you so much for watching. I'll see you in the next one. Cheers.